All right. So today we are going to be talking about the response of general RLC circuits. So when we had a parallel RLC circuit, where we had some current IS, some resistance RS, and then a switch that could either open or close with a resistor R, an inductor L, and a capacitor C. Let's just say, for the sake of argument here, that the switch is opening up at t is equal to 0. We were able to develop a differential equation as a function of that capacitor voltage, Vc of t, right? We did that by taking each of these three currents, IR of t, IL of t, and IC of t, and expressing them in terms of Vc of t. The result was something of the form A S squared plus 1 over RC times S plus 1 over LC e to the ST was equal to 0. And from this equation, we found that alpha, our Neper frequency, was 1 over twice RC, which is exactly 1/2 of the coefficient B in this quadratic equation, right? Where the coefficient, let's say this guy right here represents B, this guy right here represents C, and then we solved the system in such a way that the coefficient A was 1, right? And we also found omega naught was the square root of 1 over LC, which is simply the square root of the coefficient C in our relationship. So for a series RLC circuit, where we have some voltage source Vs connected to some resistor Rs, and then a switch, again, we'll say opens at t is equal to 0. And we had a resistor R in series with an inductor L in series with some capacitor C. We had an inductor current, IL of t, that was our common signal over all of our elements. And then we defined our voltages, VC, VL, and VR, like so. we found that in developing our second order differential equation for this guy, we came up with a relationship A times S squared plus, I'm trying to remember if it was R over L or L over R. R over L. S plus 1 over LC e to the st is equal to 0. And if our coefficient of the S term is B, the coefficient of our constant term is C, again, we saw that alpha was R over 2L, which is the exact same thing. Oh, sorry, that shouldn't be 1 over B. That should be B over 2. I don't know what the heck I was thinking there. B over 2 as well here. And omega naught, still 1 over root LC, or the square root of C. All of this to say, we can easily see that our Neper frequency is simply 1/2 the coefficient on S in our second order differential equation, or characteristic equation. And C is simply the square root of the constant term in our characteristic equation. So from that, we should be able to infer pretty easily that for a generic RLC circuit, which is not strictly in parallel, or the resistor, capacitor, inductor are not strictly connected in parallel, nor are they strictly connected in series, if we can figure out what our characteristic equation is, we can then use these coefficients B and C to determine the quantities alpha and omega naught, and then tell whether that system is behaving as a critically damped, overdamped, or underdamped system. So what we're going to spend the next bit talking about is how to get our differential equation. And unfortunately, it's going to be different for every single circuit that we deal with. Okay. So let's say that I have the following circuit. I have a switch that is closing at t is equal to 0. When that switch closes, it's going to short out a resistor that I am going to call R2. And we will have this resistor here, R1. Some voltage source, I'll call it Vs. An inductor L, a resistor R3, and finally over here, some capacitor C. And I'm going to define the following quantities. The voltage drop over my capacitor will be Vc of t. The current flowing through my capacitor will be Ic of t. The voltage drop over my inductor will be VL of t. The current flowing through my inductor will be IL of t. And let's specify the values of our elements. Our source voltage is 24 volts. L will be 2 henries. C will be 1/5 of a farad. R1 will be 4 ohms. R2 will be 8 ohms. And R3 will be 12 ohms. All right. So let's start with what I hope is pretty obvious. Why isn't this a series RLC circuit or a parallel RLC circuit? Buddy. Right. So if we looked, like if we ignored what I have my hands over here, this looks very much like a series RLC circuit because we have an inductor L in series with resistor R3 in series with that capacitor C. But the inclusion of this other stuff during the transient condition for the dead network, we have this resistor R1 that is going to be in parallel with the combination of L in series with R3, which means it cannot be combined into any of the other resistors. So this guy is definitely not going to behave like a simple series RLC circuit. Is close, but it's not the same, okay? So we are going to have to spend some time developing our differential equation here, all right? So we can approach this in several different ways, all right? During the transient condition, our resistor R2 is shorted out, right? So I could say that I have a current IR1 of T and it will flow through the short circuit during the transient condition such that IR1 of T is equal to IL of T plus IC of T. Anybody have a problem with that? All right. The simple application of Kirchhoff's current law at the node where the resistor R2, the inductor, and the capacitor are all connected together. We could just as easily express IR1 of T as our source voltage Vs minus Vc of T divided by R1. And why that's important is because I can do some simple manipulation here and effectively get rid of what my ultimate goal is here. Maybe this will help explain what I'm about to do. My ultimate goal here is to get a second order differential equation as a function of either the inductor current or the capacitor voltage. Okay, so everything in terms of either IL or VC. Okay, so for instance here, if I substitute this value in for R1 or IR1, that's leaving me with constant minus one of the two quantities I'm interested in divided by a constant is equal to one of the quantities that I might be interested in plus something related to the derivative of a quantity that I might be interested in, right? So it's going to be these substitutions here that are going to kind of guide our analysis. So I can say that let's do one more thing here. Let's say that IC of T is C dV by dt, which we know has to be true for any capacitor. And we can kind of combine these three equations together to find that Vs minus Vc of t divided by R1 is equal to IL plus C dVc by dt. And if we were so inclined, we could rearrange this guy ever so slightly and find that we would have IL of t plus Vc over R1 plus C dV by dt is equal to Vs divided by R1, if I've got my algebra correct here. I will tell you, I know that I tend to make a lot of algebraic mistakes making these substitutions and all that kind of stuff, so it's very important that after pretty much every step, we go through and make sure that we haven't made any silly mistakes, because it's going to be very easy to allow that mistake to propagate on much further into the problem, which will mess everything up, right? So all that I've tried to do here is move the quantity Vc divided by R1 to the right-hand side. So I have IL plus Vc over R1 plus C is equal to the constant term. And then I guess just switch the sides, okay? So we have an equation right now where we have two of the quantities of interest. So we need to figure out some other way or some other relationship in our circuit to where we can express IL in terms of either Vc, the first derivative of Vc, or the second derivative of Vc in order to do a substitution in here. So anybody have any thoughts on where the hell we might get some other relationship? Let's look back at our original circuit here.
The voltage across the inductor is going to be Vc minus voltage across R3.
Okay, so what Ian is suggesting is I'm going to interpret it as we can apply Kirchhoff's voltage law around this loop, which will in some way relate our current IL to our voltage Vc. Does that seem reasonable? So we could say, let's call this guy for now equation 1. So we could say that Vc of t is equal to VL of t plus R3 times IL of t. So that's nothing more than the potential difference between this point and this point is the capacitor voltage, or the sum of the inductor voltage and the voltage drop over the resistor, with the positive polarity for the resistor voltage drop on top. And since we know that VL of t is L di by dt, we can substitute that guy in, and we find that Vc of t is equal to L di by dt plus R3 IL of t. All right, so let's call this guy equation 2. And let's look what we've got here. So if I look at equation 1, I have IL of T, something I want, plus VC of T, where I just figured out how to express VT in terms of IL and the derivative of IL. So that's kind of taken care of. Plus C dVC by dt. So how do I figure out how IL relates to the derivative of the capacitor voltage? Take the derivative of equation 2, right? So if I take the derivative of equation 2 with respect to time, I can easily see that the derivative of the capacitor voltage is going to be L times the second derivative of the inductor current plus R3 times the first derivative of the inductor current. And I can now substitute equations 2 and 3 into equation 1, leaving me with IL of T plus 1 over R1 multiplied by L times DIL of T by dt plus R3 IL of T plus C, and now I'm substituting in equation 3, L d squared IL of T dt squared plus R3 DIL of T by dt is equal to Vs over R1. And now we just need to group together terms to figure out what our coefficients and all that kind of stuff are going to be, right? So what's the coefficient of my second derivative term going to be? LC, right? So I'm going to have LC times the second derivative of my inductor current. Then I want my first derivative bits. There's going to be several of these guys, right? So I definitely have a term that is L divided by R1. Then I'm going to have a term that is C times R3. Times the first derivative of my inductor current with respect to time. Then I'm going to have my coefficients for my 0th derivative of IL, right? So that's going to look like a 1 from the left-hand side. Then I'm going to have an R3 over R1 term. Did that take care of everything? Let's double check just for the sake of argument here, right? So the second derivative term only shows up once. I have this L out in front that's being multiplied by the C that's getting distributed. So that's where that LC came from. So that seems legit. I see the first derivative show up twice. So I should have 2 total terms. This guy, I have an L that's being multiplied by the 1 over R1 that's being distributed. So that's where this comes from. Over here, I have an R3 that's multiplied by this C, which is where this term comes from. For my 0th derivative, I have an IL by itself out here, which is where this 1 comes from. And then I also have this IL, which is multiplied by R3 and then divided by R1. So that's where this part comes from. And then finally, this is all equal to the constant on the other side. So there's really only one more step we have to do here. Brandon, what do you think it is?
So
Not even that far, right? Let's go back to what we looked at previously. Okay. Our differential equations had a constant value or characteristic equation where effectively S is substituting for the derivative of S is the derivative of our coin. We had a coefficient of 1 on the S squared term, which means we need a coefficient of 1 on the second derivative term in each of these cases. So we simply just need to divide by LC, right? So that would give us the second derivative of IL by dt plus, and we can be lazy here, L over R1 plus R3 over C, all divided by LC times the first derivative of the current plus 1 plus R3 over R1 divided by LC IL of t is equal to VS over R1 LC. Dang it, kept scrolling up. Go back one page. And so hopefully we can all easily see that this guy right here is B. This guy right here is C, which will now allow us to calculate alpha and omega naught. So let's calculate alpha and omega naught here and see what kind of circuit this is. So we're going to have 2 over R1, so 2 over 4 plus R3, which was 12 times 0.2. That whole thing divided by L times C, so that's 2 times 0.2. So I get B is equal to 7.25. C is 1 plus R3, so that's 1 plus 12 over 4 divided by L times C. 10. And so from this, alpha, which is just 1/2 beta, is 3.625. Nepers per second. And omega naught is then just going to be the square root of 10 radians per second, where the square root of 10 is 3.162. So now that we've calculated alpha and omega naught, is this circuit critically damped, overdamped, or underdamped? Overdamped. Since alpha is greater than omega naught, it's an overdamped circuit. And then from here, it's just the exact same things that we've done previously. Caleb, what's up? No. So if we scroll up here, maybe I. No. Yeah. So yeah, omega naught is just the square root of C.
What are these, the B and C, what is that?
So B is the coefficient of the first derivative term. C is the coefficient of the 0th derivative term. And A, which is 1, is the coefficient of the second derivative term. So effectively, what we would wind up doing here is put in our guess value of IL is AE to the ST, blah, 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 and we'd wind up having exactly a second order polynomial in terms of S, where this guy would correspond, this coefficient would correspond to what's in S, and this coefficient would correspond to the constant value term. So we're just skipping that step and saying the first, the coefficient of the first derivative term is B, the coefficient of the 0th derivative term is C. By 0th derivative, I mean we just don't take the derivative of it. And that allows us to directly calculate alpha and omega naught, which is what we did for our series RLC circuit and our parallel RLC circuits. So we're taking our previously gained experience of deriving the response equations for those two well-behaved types of systems and applying it in a more general sense to really any second order circuit, right? So this one that we just worked had an inductor and a capacitor. But we can work another one where we have two inductors that can't be combined or two capacitors that can't be combined, and we can apply the exact same rules. So the question here then becomes, do we need to go through the motions of, now that we know that this is an overdamped system, do we need to actually solve for any of those four quantities, or do we know enough about solving RLC circuits in general to move forward? Because once we get to this point, it's nothing different than what you've done. Once you know alpha and omega naught, you have enough information to calculate S1 and F2 if necessary, or omega D if necessary. You know how the system behaves. And then it's just simple DC circuit analysis techniques to figure out what's going on at T is equal to 0, T is equal to 0 minus, T is equal to 0 plus, and T is equal to infinity. Okay. All right, so let's work another one of these guys. Let's say that we have the following circuit, and this time we're only going to be interested in just getting to our differential equation. Some source voltage Vs connected to a switch that's closing at T is equal to 0. We have some resistor R1 and inductor L1. So I'm going to call this voltage V1 of T. R2. Here is a voltage VL, excuse me, V2 as a function of time. And I'm also going to define my inductor currents. Like so. So I want you guys to throw some stuff at me. Okay? We can effectively, it's not necessarily the most efficient thing to do, but we can kitchen sink these problems. And by that, I mean, we just throw anything and everything that we can think of at it and kind of see what sticks.
V1, V2 plus RI2. Just the
Okay,
L1 parallel with R2.
all right, so you're saying we could write a KVL equation around the right-hand loop, okay? So V1 of t is equal to V2 of t plus R2 times I2 of t, okay? So right now, this equation only has three terms, but only one of them is expressed in terms of something that we can actually use, right? Because these are we have two inductors. We are going to want a second order differential equation in terms of either I1 or I2, right? So Sarah, what do we do to change those voltages to something useful, which are our inductor currents? Right. So the voltage drop across an inductor is simply the inductor value times the derivative of the current. So we could easily go ahead and say that L di1 by dt is equal to L di2 by dt plus R2 I2. Oh, sorry, I should have L1, L2. Thank you, Ian. Very good catch. That would have made it difficult. All right, Mr. Bodie. What do you think we should do next? Okay. Alexis, what are your thoughts? Okay, so a relationship with the currents. That sounds wonderful. Care to elaborate?
Creating like equations for isodality so as to find the derivative of it.
I don't know that I agree with that yet. And so we could definitely take the derivative of this guy, which would tell us that the second, L1 times the second derivative of inductor current 1 is equal to L2 times the second derivative of inductor current 2 plus R2 times the first derivative of inductor current 2. But that's not really helping us because that's just kind of the same relationship expressed in the same way. So we need to figure out, what we're trying to do is to figure out another relationship that relates I1 to I2, or the derivative of I1 to I2, or the derivative of I2 to I1, or something like that, right?
So is VS over R1 equal I1T plus I2T?
Not quite, but very close. Okay. So VS over R1, you're trying to do Kirchhoff's current law at this node, right? Which is exactly what we did with the last problem. There's nothing remotely wrong with that, except that the voltage drop over R1 isn't VS because this terminal of R1 isn't shorted to the negative flared terminal voltage source, right? So it should actually be VS minus V1, which is the total voltage drop over R1, is divided by R1 is equal to I1 plus I2. So KCL would be VS minus V1 over R1 is equal to I1 plus I2. So to make this slightly less awkward, what could we do here? VS is going to be equal to V1 over R1, right? Where V1 over R1 is L1 over R times the derivative of I1. So I'm just moving this to the right-hand side of the equal sign and using the exact same relationship here. So we know that V1 is L1 times the derivative of I1. So we just need to multiply this guy by a factor of 1 over R1. Does that make sense? So that is 1 over R1 times L1 dI1 dt plus I1 plus I2. Okay. So we now have, let's call this guy equation 1. So this guy here could certainly be useful, but we need to kind of rearrange things a bit, right, Ian? Or actually, you're not. I'm trying to remember your name. I want to say it's Wesley Granger, but that's the wrong class. Jacob. I apologize for not remembering your name.
When you need more clarification on R1, because it's also divided by R1.
Oh, thank you. So let's be lazy and do that. Thank you. So I messed up my algebra. Told you I was going to do it. All right. So the problem that we're facing here, which I believe is easily solvable, is that we can't substitute this guy. Well, I guess we can. So we can substitute this guy into this guy, right? Because we know exactly what L di1 by dt would be. But so the problem there is we're going to get a derivative of I2 plus a 0th derivative of I2 plus I1 plus I2. So we're going to still need some other relationship to get rid of that I1 that's going to be introduced there. And ostensibly, we could divide both sides of this guy by L1 and then integrate the derivative. But then we're no longer going to have a second order differential equation. We're going to have an integral differential equation that's going to be all awkward because we're going to have initial conditions to throw into the mix. So I'm going to say, let's leave this guy alone. So Brandon, what can we do to this guy to effectively isolate a variable?
We're going to isolate I1, right?
Yeah, so we want I1, all of the I1 terms on one side, all of the I2 terms on the other side of the equal sign. Yeah, so we can just subtract these terms. So we'd have negative L1 over R1 di1 by dt minus I1 plus Vs over R1 is equal to I2. So now we have I2 expressed only in terms of I1 and its first derivative. We can take the derivative of this guy to get the derivative of I2, right? So let's call this 2. So how do I take the first derivative of this whole equation? What's going to happen? Sonny, I haven't picked on you today.
Whole equation.
First derivative of both sides of this equation with respect to time. So what happens when I take the derivative of the derivative? Second derivative, okay? So we're going to have negative L1 over R1 times the second derivative of I1 with respect to time. What happens when I take the derivative of I1 with respect to time? I get the derivative, right? Justin, what happens when I take the derivative of ds over R1? So Vs is a constant value voltage source and R1 is a constant value resistor. So the ratio of Vs over R1 is a constant. What's the derivative of a constant? 0. There we go. So that bit goes away. And we now have the derivative of I2 with respect to time. Let's call this equation 3. And we can easily see now that we can substitute 2 and 3 into equation 1. And then several algebraic steps later, we would have our second order differential equation. We could actually do stuff like apply nodal and mesh analysis to these too, because those are not, all we've done in this particular problem is KCL and KVL. So should stand to reason that since mesh is multiple applications of excuse me, KVL, that should be fair game. And since nodal is multiple applications of KCL, that should also be fair game. So if you wanted to do something like that, you're absolutely capable of doing it. You just then have to think of, okay, well, how do I relate those mesh currents to the inductor currents, right? Because a mesh current represents a current flowing around a loop, not so much a current flowing through a particular circuit element. Similarly, if you were going to do nodal analysis, you'd need to figure out how to represent your nodal voltages with capacitor voltages, right? Or I guess technically, you could represent them with inductor voltages and then thereby inductor currents and so forth. All right, so do we need to go through the algebra of combining all of this junk again? All right, so this is general RLC circuits. That's enough out of me for today. What we're going to do on, today is Monday, right? Yeah, so what we'll do on Wednesday is we'll take one of these guys and work it all the way through from tip to tail based on your input solely. And then that'll be the last thing that we have to do with these RLC circuits. When is our next test supposed to be? Friday. All right. So Wednesday will also be a review apparently. All right. See you guys on Wednesday.